Hi everyone. So today we're going to be talking about section 7.4, which is going to be integration of rational functions by partial fractions. Now we're going to need to recall this topic that was learned somewhere along college algebra or pre-calculus, which was known as partial fraction decomposition. Now, it's known as partial fraction decomposition simply because when we have this fraction, say we had 2 divided by x minus 1 minus 1 over x plus 2, one of the questions that we would ask is, what does this simplify to be? Alright, so what this simplifies to be turns out to be x plus 5 divided by x squared plus x minus 2. Now, in terms of which way we want to observe, now moving from left to right, that's just algebra. In other words, it's pretty straightforward to just go ahead and combine like terms. Once you're able to get the denominator to be the lowest common denominator, everything just combines. Now, the part that we want to focus on is moving backwards, right? Everything in math, if we go in one direction, we must be able to go back in the other direction, which means this direction is your partial fraction decomposition. All right, I always abbreviate it to be PFDC. PFDC. So if you ever hear me mention PFDC, it means that I'm wanting to do this by partial fraction. All right, and here's the reason why we want to focus on this partial fraction decomposition. So say that we looked at that example that we just saw here. And within the example, say that I wanted to integrate x plus 5 divided by x squared plus x minus 2 with respect to dx. Now, we could try to make a substitution, we could try by parts, we can even try trigonometric substitutions, and we're going to wind up at the same spot at all times. The same spot meaning that if we were to look at this using partial fraction decomposition, it would be a little bit more direct, or in other words, a little bit easier. Simply because if we use partial fraction decomposition, this first term here and this second term here now turn into substitutions for the integration of a natural log, which means for the first integral, we would get something along the lines of 2 natural log of the absolute value of x minus 1. For the second integral, we would get minus the natural log of the absolute value of x plus 2, and then we would get some constant. In other words, this here, the second integral, is easier to evaluate. But the thing is, how do we get there? And the way we get there is with partial fraction decomposition. So now we want to get to a place where we can start using partial fraction decomposition a little bit more direct or a little bit more natural in a certain sense. So let's go ahead and let's look at this example really quick. So on this example, we want to find what is the integral of x cubed plus x divided by x minus 1 dx. Now you might say, hey, we can start jumping straight into partial fraction decomposition, but I'm going to caution you there. Partial fraction decomposition only works or can only be applied if the degree of the numerator is less than the degree of the denominator. So polynomial-wise, or term-wise here, rational function-wise, the numerator is not less than the denominator, which means we have to go through long division. So let's go through long division first. Use long division. All right, so here we go. Using long division. I'm going to have x minus 1, and this is going to divide x cubed plus 0x squared plus x, and then plus 0 for that constant. All right. How many times does x go into x cubed? Well, we kind of need x squared of them. So x squared times x, that's going to get us x cubed. X squared times 1, that's going to get, or negative 1, x squared times negative 1 is going to get us negative x squared. So that's going to be negative x squared. Subtract these two. The first term cancels automatically. The second term, that negative gets distributed, and it now turns into a plus. Which means for the second term now, we're going to bring everything down. That's going to be x squared. Bring this next term down, plus x. Now we got to figure out x to get into x squared needs just 1x. So x times x gets us x squared. X times negative 1 gets us negative x. Here we are. Now I subtract all this. Subtracting all this, the first term is going to cancel out. Second term, negative distributes. Now we're left with a plus, which means we get 2x. And then we can bring down this 0, but then we would get 2x plus 0. So for the last piece, what we need to do is we need to figure out how many times does x go into 2x? Well, that's going to be 2 times, so we enter plus 2. So 2 times x gets us 2x. 2 times negative 1 gets us negative 2. Subtract out. First term is going to cancel. Negative distributes. And now we finally get positive 2. So the way this looks like at this point in time is that this integral, the integral of x cubed plus x divided by x minus 1 dx, should look like the integral for x squared plus x plus 2 plus the remainder divided by the divisor, which is x minus 1. And this is all dx. Now you could then see we can now integrate this term by term. The integral of x squared we can find easily. The integral of x, again, quite easily. The integral of 2, straightforward. And finally the integral of 2 divided by x minus 1. That one might not be so easy, but it's completely fine because we can use a U substitution for a natural log integration. So in here, let's go through. This is now going to be x cubed over 3 plus x squared over 2 plus 2x plus 2 times the natural log of the absolute value of x minus 1 plus c. And there you have it. So again, for this example, we didn't need to use partial fraction decomposition, which is kind of a good thing. But then at the end of the day, we still need to rely on long division. How can we break these functions down, or how can we break these rational functions down in order for us to be able to approach the integration with any techniques that we've learned so far? All right, now I'm going to write down the 4 partial fraction decomposition scenarios that we are going to be using. All right, so the 4 cases of the partial fraction decomposition that we're going to be using are here. Partial fraction decomposition. Again, in order for us to be able to use partial fraction decomposition, we need to be aware that the degree of the numerator, r of x, must be less than the degree of the denominator, which is q of x. Now, polynomial-wise, again, we just need to look at their exponents on the variables. What's the highest exponent? what's the highest degree, in other words, what's the highest exponent value on each of these, or on each of the variables in the numerator and denominator. We compare the two highest values. That tells us the degree of the polynomials. Now, for the first case, when we look at the denominator, once we've figured out that this is satisfied, the denominator is then going to tell us what kind of case we have. We're going to need to factor the denominators at all times. So another thing that we need to focus on is that we need to factor denominators. And we need to do this at all times because, again, it's going to let us know what case we have. The case of linear factors, if we have a linear factor that is not repeated, then we use case 1. If we have a linear factor that is repeated, we use case 2. If the denominator is an irreducible quadratic means that it does not factor, over the integers. If it doesn't factor over the integers, again, we're going to be looking at this particular case where we have to set up every single factor in this particular form. Looking at the very last case, if our denominator is an irreducible quadratic, which is repeated, in other words, we're able to factor it into a quadratic form, but then we get multiple values of it. All right. In that sense, we then need to use case number 4. So I'm going to be referring back to these cases as we go through the course and as we go through this particular section. And one thing that I want to mention, that just because we have 4 cases doesn't mean that our problem will only include one case. It's quite possible that one problem could use all 4 cases. So it could use all 4 cases in one problem. We just have to be able to make sure that we always account for that case when it happens. All right. Now for this section, I am also going to use one more item. And this item we learned back a few sections ago when we're looking at something like this. This turns into 1 over a times tangent inverse of x divided by a plus your constant. We're going to need to make sure that we use this throughout this section. All right, so let's go on to these wonderful examples. So here's your first example. We want to find the integral of 1 over, the integral of 1 over x squared minus 7x plus 10, and this is all going to be dx. All right, here we go. So because the fraction is automatically in a rational expression form, what I want to do is I want to factor. So let's start off by factoring this. Denominator. We're going to look at the denominator and we're going to say, okay, well, looking at the denominator, it looks like it factors, and it looks like it kind of factors into something along the lines of x minus 2 and x minus 5. Numerator stays exactly as is. Now we have to go through the method of partial fraction decomposition to break it apart. So at this point in time, we cannot do a direct integration. Because we can't do a direct integration, we then have to go to partial fraction. So let's start doing the work for partial fractions. I'm going to do this work in purple, that way we can see it in a different color. All right, so partial fractions, let's see what kind of cases we satisfy here. So looking at the denominator is 2 different linear factors. So two different linear factors that are not repeated, which means this falls under case number 1. All right, that we have distinct linear factors. So because we have these distinct linear factors, I'm going to use that. I'm going to say 1 over x minus 2 times x minus 5. All of this is going to break down, using this piece of information, into these individual coefficients in the numerator. So it's going to be some a coefficient over x minus 2 plus some b coefficient over x minus 5. Great. This is the method of partial fraction decomposition that we want to work with. Now what we're going to do is we're going to multiply both sides by the LCD. So let's go ahead and let's multiply both sides by the LCD. So multiply by the LCD. And the LCD is actually quite nice here because we've already kind of inadvertently found it, which means we're going to get 1 is equal to a times x minus 5 plus b times x minus 2. There we are. All we have to do is figure out what is a and what is b. Easier said than done, but we'll work with it. All right, so here we go. This is my favorite method to use. What I'm going to do is I'm going to distribute on the right-hand side. So I'm going to go ahead and start distributing. This is going to be ax minus 5a plus bx minus 2b is all equal to 1. Right-hand side, I have x's, so I'm going to group those together and factor out the x. So factoring out the x, I'm going to be left with a plus b, which is multiplied by x. And then as a constant, I'm going to be left with minus, or let's say plus, in this particular case, minus 5a minus 2b. All right, and all of this is equal to 1. Now what we're going to do is we're going to start comparing left side to the right side. So on the left-hand side of this equation, do we have any variables of x? Well, just by looking at it, no, we do not. Which means, in this case, this is going to tell us that a plus b must be equal to 0. Because again, we have no x's on the left-hand side. Now the right-hand side, we do have a constant on the right-hand side. That constant on the right-hand side is this, and it must be equal to this constant. Which then means that we get negative 5a minus 2b to be equal to 1. And that's under this result that we had from up here. All right, that was that piece, and that was that piece, or vice versa. So all we got to do is solve here. We have a system of two equations. We must solve it. So system of two equations. So let's solve. All right, we got to find a and we got to find b. Well, using the first, let's say, equation, we get that a is equal to negative b, which means that we get negative 5a, which is negative b, so negative 5 times negative b minus 2b is equal to 1. Negative times a negative is a positive. This means that b is going to be 3b is equal to 1. Naturally, this will produce that b is equal to 1/3. Nice. So we get that b is equal to 1/3. What does that mean, or what does that imply for a if they must cancel out to 0 when we're adding them? That's right, Chef Gordon Ramsay. It's negative 1/3, which must be a. So now that we have this, we can then go through and say, well, our partial fraction decomposition now will then guarantee us that we get negative 1/3 divided by x minus 2 plus the b value, which is 1/3, over x minus 5. And that's really all we need, folks. Simply because now we have that, and we can come now to this integral and say, using this integral, I can now integrate negative 1/3 divided by x minus 2 plus 1/3 divided by x minus 5, and that's going to be dx. Now, making a U substitution, we can do a U substitution for the denominator, each independently, which then means that for the first term, we're going to get negative 1/3 times the natural log of the absolute value of x minus 2 plus 1/3 times the natural log of the absolute value of x minus 5, and then we get our constant plus c. And this is the final answer that we want to see, or in this case, that I want to see. All right. Again, the hardest work is the actual partial fraction decomposition. The nice aspect about this is once you deal with that partial fraction decomposition here, all this stuff in purple, then going over here, the evaluation should be pretty straightforward. It should be either some natural log, some direct integration, or even some up here of tan inverse integration. All right, so we have to be careful with that. Now, this was the first example. One thing that I want to key in on as well, let's look at the degrees. What is the degree of the numerator? Degree of the numerator is 0 because there is no variable with an exponent. In other words, it must be x to the power of 0. Looking at the degree of the denominator, the degree of the denominator for this example was 2. Which one is larger? Denominator. Which means we could apply partial fraction decomposition. It will work. Yay, it works. That's a happy face, by the way. All right, so it works. Now, we're going to have to check this every time before we actually start the problem. All right, so we're going to go on to the next example. All right, so let's go through this example. This example says that we need to evaluate this integral given by the numerator being x squared plus 2x minus 1 divided by, and then the denominator is 2x cubed plus 3x squared minus 2x. And this is all going to be with respect to dx. Now again, the first thing that I said before is that we want to make sure that we can factor this. So that's the very first step that we're going to take here, is we're always going to factor. So let's look to see if we can factor this. If we can factor out a numerator, great, that's awesome. If we can't, then, too bad, and it's okay. Denominator, I see an x that we can factor out of that denominator. After we factor out the x, we're going to be left with 2x squared plus 3x minus 2. And this is all with respect to dx. The denominator looks like it can factor just a little bit more. So that's x squared plus 2x minus 1. And then that's going to be x times, that's going to be somewhere along the lines of 2x minus 1 times, it looks like it's going to be x plus 2. And then we can verify this, and that's all dx. All right. So just do a really quick verification. Make sure that this leads us to the right result. Positive 4, negative 1. That's positive 3, negative 2. Great. Awesome. Now, we're going to really quickly make sure that the degree of the numerator and the degree of the denominator are being compared. That way we know what to choose or what to proceed by. Degree of the numerator, as we can see here, the degree of the numerator is 2. Degree of the denominator, we have x, 2x, and x, but by the multiplication property, we're going to have 3, which means the degree of the denominator is greater than the degree of the numerator, so we can proceed with partial fraction decomposition. So partial fraction decomposition, here we go. PFDC. So we're going to take what we have, that x squared plus 2x minus 1 divided by x times 2x minus 1 times x plus 2. And we're going to see that the denominator just uses a whole bunch of linear factors. Linear factors that are not, these are not repeated, meaning I don't have multiple of those factors. Now, because I don't have multiple of those factors, that's going to be perfect for me, which means the first linear factor is just x, so I put an a over x. The second linear factor is b, and that's going to be 2x minus 1. And then the third linear factor is just going to be c over x plus 2. Once we have this, we're going to multiply by the LCD. And we're going to do this onto both sides. So multiplying onto both sides by the LCD should leave us with x squared plus 2x minus 1 is equal to a times 2x minus 1 times x plus 2 plus b times x plus 2, and then plus c multiplied by x multiplied by 2x minus 1. So here's what we have so far. Now what we're going to do is, on the right hand side, again, I'm going to start distributing everything. Start distributing all of your terms, all of your coefficients, and start grouping them together. Alright, so here I'm going to have a multiplied by 2x squared, alright, plus 3x minus 2. There we are. The second term is going to be b times x squared plus 2x, plus the next term is going to be c times 2x squared minus x. There we are. Now we're going to distribute those coefficients. Distributing the coefficients now, this is going to get us 2ax squared plus 3ax minus 2a plus bx squared plus 2bx plus 2cx squared minus cx. Alright, awesome. Now I'm going to start grouping all of my like terms together. So my like terms, I see I have an x squared and x squared here and an x squared here. So naturally, what I'm going to have is 2a plus b plus 2c. All of these contain that x squared term. In other words, all I did was factor out the x squared from all of those like terms that I had selected there. Next, I'm going to do the same thing with the x values, or the x variables. Let's look at the x variables. Alright, so I see an x variable here, I see an x variable here, and I see an x variable here. Using those three, I'm going to factor out the x variable to get me 3a plus 2b minus c, and that's multiplied by x. Anything that's left over is a constant. And I believe we only have one left over. That's a constant, so that's minus 2a. Now, the reason I'm doing this is because on the right-hand side, on the left-hand side, I'm left with x squared plus 2x minus 1. All I have to do now is, because both of these sides are equal, all I have to do is basically compare coefficients. These coefficients are multiplying the x squared, which means that's going to multiply the x squared value. In other words, the coefficient here is 1, which means 1 must be equal to 2a plus b plus 2c. Comparing the coefficients, 2 multiplying the x on the left-hand side must be this coefficient multiplying the x on the right-hand side, which means 2 must be equal to 3a plus 2b minus c. The last one is going to tell us that we have a -1. That -1 constant is going to be equal to this constant here, which means for us that -1 must be equal to -2a. What does this then tell us? Well, this then tells us that we have a system of equations. And we need to solve. So let's go through the solving techniques here. All right. Now, for the first one, for the equation down here at the bottom, we automatically get a really nice answer for that equation. We get that x is going to be equal to a is equal to 1/2. Nice. All we need is b and c. All right. So I want you to take some time and I want you to find what is b and what is c. So again, take some time, do that for yourself. Pause the video if you need to. All right, so you should have gotten these values. Once you're able to solve, you're going to get that b is 1/10 and that c is going to be -1/10. Now that we have this, we can go through and we can make our substitutions now into our partial fraction integral. That partial fraction integral we're going to take from up here, and we're going to make those insertions. A, which was 1/2, that's 1/2 divided by x, plus the b value, which was 1/10, so it's going to be 1/10, is going to be divided by 2x minus 1, plus -1/10 divided by, that's c divided by x plus 2, which was -1/10 divided by x plus 2, and this is all dx. Now you're going to see that the denominators are all going to be values that we get for these specific integrals. All right, so really quickly I'm going to put pause. And now as I'm looking at this, I realized that there was a mistake made here, so I'm going to go back and I'm going to correct my mistake. The mistake happened when I considered b to be 1/10. B is not 1/10. B is actually what I have as 1/5. So b is 1/5. So I'm going to make that adjustment here. My apologies. There we go. So my apologies on that. Now, again, we're going to work with some U substitutions here. For the first integral, we're going to get 1/2 multiplied by the natural log of the absolute value of x. The next integral, it is going to be 1/5, but since the denominator is multiplying by 2 times that x, we're going to need a U substitution, and we're going to need to account for that too, which means we will get 1/10 multiplied by the natural log of 2x minus 1, plus, or sorry, minus, in this case, minus the natural log, goodness gracious here, minus 1/10 times the natural log of the absolute value of x plus 2. And that's all plus the constant c. So this is what we get in this particular case for this question. And again, this all started with, can we perform this with partial fraction decomposition? The answer is yes, therefore we go ahead and take that approach. Awesome. So let's go through a different example now. So this next example, what we're going to have here is that we want to evaluate the integral for 3x minus 9 divided by x minus 1 times x plus 2 quantity squared, and this is all dx. And again, we want to make sure the degree of the denominator and the degree of the numerator are in proper comparison. So the degree of the numerator versus the degree of the denominator, let's see, degree of the numerator is 1, degree of the denominator that's x squared, so that's 2x's already. All right, x to the power of 2 multiplied by another x, adding the exponents, that's going to give us an exponent of 3. Degree of the denominator is larger, so we can use partial fraction decomposition. And we're going to jump straight into partial fraction decomposition. All right, so let's proceed by partial fraction decomposition at this point in time. Now, the nice part about this particular case is that the denominator is already factored for us. And because the denominator is already factored for us, all we then have to do is consider what is then the outcome according to our cases. Now, you're going to see that the first factor, x minus 1, is a linear factor, but it's non-repeated, which means we're going to get some numerical value up top, some a value. But then you're also going to see that x plus 2, that is a linear factor, but that linear factor is repeated, which means we have to make sure that repetition takes place for that repeated linear factor. Notice I repeated it. If it's a repeated linear factor, you have to repeat it in the denominator, much like that sentence. All right, so I'm going to multiply both sides by the LCD, so multiply by the LCD. Once we multiply by the LCD, we can smooth this out to be 3x minus 9 is equal to a times, that's going to be x plus 2 squared, plus b times x plus 2 times x minus 1 plus c times x minus 1. And once we have this, then we can go through and start distributing all of our terms, all of our factors here. All right, so let's go with this. This is going to be a times x squared plus 4x plus 4 plus b times, that's going to be x squared. That's going to be 2 minus 1, so that's going to be plus x minus 2. And this is going to be cx minus c. Perfect. Let's distribute the coefficients now. ax squared plus 4ax plus 4a plus bx squared plus bx minus 2b. And we still have the plus cx minus c. Nice. Now that we have all of our terms distributed, all of our factors distributed, we're going to go ahead and we're going to start combining these like terms. Anything that has an x squared, I'm going to consider together, and I'm going to factor out that x squared, which means I'm going to be left with a plus b multiplied by x squared. Then I'm going to have all of my x variables, singular x variables together, and I'm going to factor out that x. So we're going to have 4a plus b plus c, multiplying x. There we are. Now whatever's left over, that's going to be our constants. So that's 4a minus 2b minus c. There we are. Now again, on the left-hand side, we're still left with this 3x minus 9. And because of this equation here, this is going to tell us that on the left-hand side, we must be left with the coefficients that match the right-hand side. So we're then going to start looking at a plus b is multiplying that x squared. Now, do we have an x squared on the left-hand side? Yeah, the answer is no, and the answer is no specifically because the x squared variable is being multiplied by 0, which naturally means that 0 must be equal to a plus b. Nice, that's the first part. All right, the next part, comparing coefficients once again. Comparing coefficients, 4a plus b plus c is multiplying x on the right-hand side, but on the left-hand side, we just have 3. Which must mean that 3 is equal to 4a plus b plus c. The last comparison that we're going to make here, is that negative 9 is a constant, and we have 4a minus 2b minus c, which is also the constant, which means by equality, the constants must be equal to one another. There we are. So we have a system of equations. We need to solve that system of equations. All right. So again, I want you to take some time, recall some of your algebra techniques. How do we solve a system of equation that looks like this? All right. So the answers that we should get here, or the coefficients, are A is equal to negative 2/3, B is equal to 2/3, and C is equal to 5. Now, once we have this, again, we're going to make sure that these coefficients get inserted into the partial fraction decomposition piece right up here. All right, we're going to make that insertion right up there. But while we make that insertion, we're going to have to make sure that we're inserting it as we're evaluating this integral. So the A coefficient was negative 2/3. That's negative 2/3 divided by x minus 1. Plus the B coefficient was 2/3. That's going to be divided by, over here, that was x plus 2. And then we have our last coefficient, plus 5, divided by, as we said here, x plus 2 squared. And this is all dx. Now, as we go through, we're going to do a simple U substitution. So the way we're going to evaluate this one here is going to be with a U sub. This one here is going to be a U sub. And this one here is not a U sub. This is actually just a power rule. All right, so taking the integral here, this is going to be negative 2/3 multiplied by the natural log of the absolute value of x minus 1 plus 2/3 multiplied by the natural log of the absolute value of x plus 2 plus this last one is going to be 5 divided by x plus 2. Oh, excuse me on there. It's not just 5, it's negative because it's a negative exponent. So that's going to be minus 5 divided by x plus 2, and we're going to have a constant here. And this is your final result. This is the answer that I am looking for. All right. So there we are. Another example down, and again, another example of how we want to use partial fraction decomposition. Now, let's look at a different one. Next example. On this next example, we're going to evaluate the integral of x cubed plus 1 divided by x squared minus 4, and that's all dx. So again, we check first degree of the numerator versus the degree of the denominator. Degree of the numerator, 3. Degree of the denominator, 2. Ouch. That's not good. That's not good because this is not the form that we want it to be in when we try to do partial fraction decomposition. Which means in order to proceed, we must use long division first. So let's go through and let's use long division. All right, here we go. We're going to have x squared minus 4, and that's going to be dividing this x cubed plus 0x squared plus 0x plus 1. And again, notice I'm keeping the placeholders there for all of the missing variables. X cubed plus 1 was missing the variable for x squared and was missing the variable for x. So I again inserted them using placeholders multiplied by 0. So now I need to get to x cubed, but I have an x. That means I need to multiply by x. X times x squared should get me x cubed. X times negative 4 should get me negative 4x. I finally subtract this out. Subtracting will ensure that I cancel out my first term, but then that negative distributes and we get a plus, which means my terms now, they become 0x squared as we're bringing this down. This one's going to be plus 4x, and then I also have a plus 1 here. All right, so now we need to go through, right? We're going to go through and we're going to see what's going to happen here. Now, to get x squared, well, we need to multiply by 0. Not too bad. All right. So we have this going on. Awesome. I think this should be it, simply because in order to multiply x squared to get me this x, I would need to divide by an x. And that kind of negates the whole process of doing long division. Which means that at this point in time, this integral that we're looking at for x cubed plus 1 divided by x squared minus 4 dx looks like the integral, and I need the quotient, which was x, plus the remainder, which was 4x plus 1, divided by its divisor, which is x squared minus 4, and this is all dx. Awesome. So now let's look at this here. This right in here, degree of the numerator is equal to 1. Degree of the denominator, it's now equal to 2. Which means we can use partial fraction decomposition, but we must only use partial fraction decomposition on this initial term. We're not going to do it on the overall integrand, but we're only doing it on this term. So let's use partial fraction decomposition now. Partial fraction decomposition. Here we go. 4x plus 1 divided by, let's factor that denominator. Would you all agree that's just x minus 2, x plus 2? Great, I would too. So that's now a over x minus 2 plus b over x plus 2. And this is because these are just linear factors that are not repeated. Not repeated linear factors, again, they only get a coefficient of either a or b or such and such. Multiply both sides by the LCD. Naturally, we'll get a times x plus 2 plus b times x minus 2. All right, let's distribute and let's group all of these like terms together. This is ax plus 2a plus bx minus 2b. Factor out the x from the like terms, so that's a plus b multiplied by x. The remainder, or what remains left over, is 2a minus 2b. That must be your constant. Now by comparison then, left side, 4 is multiplying the x. Right hand side, a plus b is multiplying the x. Therefore, 4 must be equal to a plus b. The constants that we have a 1 and we have a 2a minus 2b. This means that 1 must be equal to 2a minus 2b. So we have a system of equations, and all we need to do is solve that system of equations. All right. You can take some time and you can solve that system of equations to see what you'll get. All right. If you want to put pause on the video right now, you can put pause on the video and solve this system of equations. All right, so the two values that we should get is that a is 9/4 and b is 7/4. And again, we're going to make these substitutions into our partial fraction decomposition that we were working with, but in this particular case, we want to make sure that we insert them using the integral that we're initially working with. So this initial piece for partial fraction breaks down into a over x minus 2. That means that that's going to be 9/4 divided by x minus 2 plus 7/4 divided by x plus 2. And that's in dx. So all we have to do then is do some quick calculations. All right. Integral of x, that's going to get me x squared over 2. Nice. Plus, do a U substitution here. U substitution, that's going to get us 9/4 multiplied by the natural log of the absolute value of x minus 2. Plus another U substitution, that's going to get us 7/4 multiplied by the natural log of x plus 2. and this is all going to be plus c because we're working with these indefinite integrals. And that should be the final answer, right? Not too bad. Not too bad considering, again, we started off and we couldn't use partial fraction decomposition in the initial integrand. Once we're able to break it down a little bit further, then we're allowed to use our methods that we have for partial fractions. Once we do that, then we're able to integrate rather easily. All right, nice. Let's work with a different example then. So here goes a different example. We want to find the integral of 18 over x plus 3 multiplied by x squared plus 9, and this is all going to be dx. All right, so again, as our methods go, we're going to check the degree of the numerator. That's 0 versus the degree of the denominator. That's, let's see, I see an x squared and x to the power of 1, so that's going to be 3. Degree of the denominator is larger, which means, hey, partial fraction decomposition, here we come. All right, so partial fraction decomposition, here we go. So we have 18 over the factored denominator, which is really nice. Now you're going to see here that the denominator for x squared, or the factor for x squared plus 9, does not factor. It's actually an irreducible quadratic. Now, because it's an irreducible quadratic, and we only have one copy of it, then we need to reduce it by one term. In other words, or by one exponent. In other words, if this was a quadratic down below, irreducible quadratic, since it's an irreducible quadratic, taking it down an exponent by 1 would leave us a linear term, and that's what the linear term is up here. And the reason this has to work is because we have something known as the division algorithm. The division algorithm will guarantee us that anytime that we divide, we'll automatically get the numerator or the remainder to be less than or equal to, exponent-wise, to our divisor. So let's multiply by the LCD on both sides. Multiplying by the LCD will then get us this here, a times x squared plus 9 times bx plus c times x plus 3. There we are. Let's distribute everything and then go through the process. 18 is equal to ax squared plus 9a plus bx squared plus, that's going to be 3bx plus cx plus 3c. Let's start grouping all our terms together. Every x squared term goes together, and let's factor out those x squareds. Every x variable goes together, and we're going to factor out that x variable, so that's 3b plus c multiplied by x. Whatever's left over, that's going to be 9a plus 3c. That stays together as a constant. Now on the left hand side, you're again going to see, hey, we're looking at a plus b on the right hand side multiplying the x squared, but then there's no x squared variable on the left hand side. So what gives? Well, that turns out to be 0x squared, which means that 0 must be equal to a plus b. And then you're going to say, hey, there's something fishy going on here as well, because there is no x variable here. Well, that means that the x variable, again, was accounted for by the 0 coefficient, which means that 3b plus c, that coefficient must be equal to 0. And then the last coefficient that we're left with is 18. That must be equal to the coefficient that we have here for 9a plus 3c. Awesome. So once we're able to get to this point, then we're going to go ahead and solve this system of equations. So we want to solve this. We need to find what is A, what is B, what is C. So take some time now and go ahead and find those values. All right, so these are the values that I get. That A is equal to 1, B is equal to -1, and then C is equal to 3. And what I'm going to do at this time is I'm going to insert these values into this partial fraction decomposition that we initially worked with. So let's go through that now. And I'm actually going to work down below here. So I'm going to say the integral of 18 divided by x plus 3. I'm just going to restate this really quickly. Over x squared plus 9, and that's all dx, is equal to the integral for the a value. The a value was 1, so that's 1 over x plus 3, plus bx plus c, that's going to be negative x plus 3, divided by, and that's going to be the denominator of that x squared plus 9. And this is all dx. Now you might say, hey, Mr. Castro, the first term, well, we can do that quite easily because it's just a U substitution. And you're absolutely right. It is a U substitution. So what I'm going to do here really quickly is I'm going to separate these integrals. That way we can see what's really taking place here, and we can dissect this just a little bit more. Just like that. All right. Now, the first integral, like you said, or that first term, was a U substitution, which means that's just going to be the natural log of the absolute value of x plus 3. Now, for the second integral, it's not as straightforward. Again, we already used partial fraction decomposition, so already used partial fraction decomposition, which means we can't use it again. All right, since we can't use it again at this point in time, let's see if we can try to break this down a little bit further. All right, or see if there's a method that we can separate this. Plus, let's see if you follow me on this. Negative x over x squared plus 9 dx plus the integral of 3 over x squared plus 9 dx. Now, are these two integrals the same? Meaning, does this integral here match these addition of these two integrals, or the addition of those two integrals? The answer should be yes. It does match the addition of those two integrals, meaning that the addition of those two integrals should be equivalent to the one integral right above. Now, since we have that, we can now perform a U substitution. U is equal to x squared plus 9, which means du must be 2x dx for this piece. Now that's going to be very nice because as we start evaluating using that U sub, that's just then going to become -1/2 multiplied by the absolute value, -1/2 natural log of the absolute value of x squared plus 9. Now for the last integral, we don't exactly need this U substitution. We can't do a U substitution. But the one thing that we can do is, if you recall, all the way at the very beginning of this lesson, there was one item here that I kind of wrote out in orange right here. The integral of 1 divided by x squared plus a squared dx can be evaluated using tangent inverse, which means we can start applying that to this integral down here. So for this integral, we're going to use tan inverse. We're going to use tan inverse of some u value. All right, so we need to find what is a, that way we can extract what we're looking at. Well, if we consider x squared plus 3 squared, then we're going to be able to extract everything that we need. In this particular case, this is going to be, this is going to be the constant of 3 in that numerator, So that's going to be the 3 from that numerator. 3 from that numerator multiplied by 1 divided by a, which is 3, multiplied by tangent inverse of x over 3, and then we're going to have a plus c. And you're going to see there that once we write that down, everything kind of just falls into place here. That's 3 times 1/3, so that's just going to be, whoa, that's going to be a whoa. Tan inverse of x over 3, and that's plus c. There we are. That is the answer to the equation that, or to the integral that we were initially looking at. Awesome. Now, that's going to be it for this particular piece for integration. There are going to be other challenging problems, but again, we'll get to those problems once we get into this a little bit more.